SwayamPrabha. Digital India. Educated India.
Hello and welcome to this manufacturing process technology part 1 module 46. Today we will be mostly talking about the joining processes, particularly the different solid and liquid state welding processes, and in that we will try to understand the physics of welding. We will also try to describe some of the associated designs that are involved in planning a welding design. So let us look at all the joining processes and why it is necessary. Okay. So, unlike the manufacturing processes employed to produce a single component, the joining processes are used to assemble different members to yield complex shapes. I think I had earlier described that when you talk about assemblies, obviously there has to be a relative orientation between the various parts or components, and for that joining is a very important issue. So, sometimes the geometries that are involved in plugging these components together are so difficult or so impossible to obtain by using only the manufacturing processes, etc. Therefore, joining processes where maybe two or more components are joined together to realize one particular link is employed for the benefit of reducing the complexity of the manufacturing processes. And so, therefore, joining is extremely important as a process. The joining of different elements can be either temporary or permanent in nature. Also, the mechanism of bonding accordingly may be either temporary or permanent. So, for example, in case of nut and bolt kind of system, which is joining, or maybe screws which are joining two members in an assembly, we can easily open or close based on our convenience, and it can be recorded as a temporary joint. Whereas something like let us say solid state welding, where there are two components which are pressurized very close to each other, so that there is some kind of a bond formulation between them, may be easily recorded as a permanent joining process. Okay. So, that is how you classify, and this is the first classification of all the different joining processes. So, we will basically describe some of the principles and the mechanisms in all such processes, and with the physical or mechanical point of view, and also some of the metallurgical viewpoints which emerge while studying such joining processes would be treated in this particular area. So, let us look at a classification schematic of the various joining processes. So, typically joining process can be classified into mechanical bonding and atomic bonding. Mechanical bonding could be again classified into more permanent or semi-permanent kind of joints, and temporary with screw elements, for example, as I just mentioned earlier. In the permanent semi-permanent category, there can be riveting, there can be stitching between two surfaces, or stapling between two surfaces, or even shrink fits sometimes, which ensures that you have some kind of a semi-permanency between the joints. That means, for example, in the case of rivets, without destroying the rivet or without breaking the rivet head open, you can't really undo the joining process. So, it is some kind of a semi-permanent intermediate kind of a joining. So, so therefore, that is how semi-permanent joints can be interpreted. Now, the other type of joining happens more on an atomistic basis, where you can have two crystals, for example, or two different materials, for example, taken so close to each other by virtue of pressure and some deformation, that there is some kind of a cold weld which is formulated within the two surfaces. So, such surfaces or such kind of bonding is also known as solid state bonding. There can be again liquid state bonding, and bonding can also be in solid and liquid state. I will just explain some of the solid state bonding. So, one of the examples, for example, could be like cold welding, where two members, two metallic plates, for example, are brought very close to each other and applied with certain pressure, so that the distances between the surfaces become almost equal to that of a grain boundary. So, there is automatically a increase in the interatomic forces because of probably the electrons of one set of atoms attracting getting attracted by the nucleus of the other set of atom, but that close proximity or close distance between the surfaces need to be coming for this kind of a bonding to take place. There can be again cases of ultrasonic welding, where you vibrate one of the components or one of the members at an ultrasonic frequency. So, that you can again introduce proximity between the members in a manner, so that there is a solid state bonding which takes place. You can also in this category introduce explosive welding. Similarly, other solid state bonding phenomena are friction welding, diffusion welding, hot forge welding, so on and so forth. In the liquid state and fusion welding processes, you typically use a source of heat, so that you are able to either melt the parent material or a different material together for introducing the bonding between the two. So, in the liquid state particularly, you can actually use an electric arc, okay, what you normally do in arc welding, and there is an arc established between an electrode and a surface, which is very high power and high power consuming, and it generates a stream of electrons which completely melts the parent materials together. So, that there is some kind of a melting and solidification, resolidification, which would ensure the bondability to be same. So, the electric source can either be an arc, where you can record this as an arc welding process. It could be electromagnetic induction causing eddy currents, which would lead to the local heating of the material, particularly metals. So, then other induction welding, or resistance welding, where there is a pressure as well as a strong current between the sheets that are being joined, or the two members that are being joined, which results in a local heat increase and a local melt pool between both the sheets. The other forms of liquid state welding, as basically the source changes from electrical to a chemical source. It could be either a hot flame produced by a gas, or by the transition metal oxides and aluminum fuel particles, together known as thermites. And the heat source in a gas welding typically is an oxyacetylene flame, which causes filler material to melt and go into the two sheets, and then it re-solidifies to formulate the weldment. So, there are other cases of particularly solid liquid state welding. For example, let us say adhesive bonding, where there is an adhesion layer which is applied between two different solid materials. So, without really changing the state of the materials into a liquid form, the adhesive layer, which itself being liquid, when it dries up, it introduces bonds between both the layers. They may be of temporary type, but that those bonds are also considered to be good enough for weldment. For example, you can actually bond plastic to metal, which is one of the key things in automotive industries, which is based on adhesive bonding. You have soldering and brazing, where again the filler material is basically taken to its melting temperature, and it generates some kind of local melts in the periphery of the weldment, and there is some degree of diffusion into of the welding zone in the periphery, which results in again resolidification and joining between both the solid members. Okay. So, these all examples of or classifications of different joining processes. So, having said that, now let us look into a little more fundamental aspect about joining processes and let us try to first classify into various schemes based on different different modalities. Let us talk about the classification of welding into autogenous, homogeneous and heterogeneous processes. In category 1, in autogenous process, no filler material is added during the joining. All the types of solid phase welding and resistance welding are booked into this category. So, there is no filler material. Then there are homogeneous joining processes, where the filler material that is used is same as the parent material. So, filler material is same as the parent material, and then obviously there are heterogeneous processes where the filler material may be completely different, is different. Okay. So, these are the soldering or brazing related processes where it may not be necessary that the filler material is same as the parent material, it is different than parent material. So, soldering and brazing for example, are two such joining processes where the filler material in one case is copper and tin and another iron and silver, and both of them are soluble in the parent material. So, therefore, there is a zone of local melt which is created inside the parent material, where there is some kind of a sort of solubility and diffusion of the liquid metal or the liquid filler, and then when it recrystallizes as one whole and joins both the sheets in this particular case, or both the members in this particular case. So, as discussed prior to this in the section on materials, we had illustrated how the bonding forces between the two metallic atoms decrease very sharply with the interatomic distance. So, obviously, as we had recorded earlier, that if the interatomic distance changes to almost a single atomic spacing, there is a tendency of the electrons of one of the atoms to be attracted towards the nuclei of the neighboring atom. So, these interacting forces are very, very large, which results in a very strong bond between the two, particularly when the two atomic species are displaced to a distance of or more or less the interatomic spacing between the lattice spacing between the two atoms of the lattice. So, the force sharply increases and attains very large value when the distance is reduced from a few atomic spacings. Thus, if it is possible to somehow bring the two metallic surfaces closer, so that nothing but the grain boundaries separate them, the two bodies will adhere with very large forces, okay, and that is what we call welding. Okay. So, how to do this and what kind of mechanisms are deployed are basically again part of solid state welding processes. So, in a solid state welding process, basically which we can carry out the welding particularly at room temperature, and obviously also at an elevated temperature, but without melting any parts. Okay. So, still there are surfaces which have solid which are solid surfaces, they do not lose their integrity, and you can basically apply pressure as well as heat here to perform the welding. So, for a better understanding of the quality of the solid phase joint, it is worthwhile to recapitulate the strength and cohesion of metals. Okay. So, a defect free crystal normally fails along a sort of a crystallographic plane where the interatomic force is the weakest. Okay. So, that is how there is a development of a crack. So, wherever there is a case where the interatomic force is the lowest value, and supposing you are now putting the object to a tensile strength, the failure would happen from that area where the bond between the materials is the weakest. What happens after the failure takes place? So, the material is separated along a cracked portion, or let us say along a small kind of a fissure, and there are two new surfaces which would come into existence, and therefore, the surface energy should increase because of the creating of two of these surfaces. Okay. And the two new surfaces which are produced would let us say demonstrate surface energy gamma, and this energy is basically defined as the work done in order to create those surfaces which you are doing externally. Obviously, you are pulling the material to get this crack initiated or get this fissure initiated between the material. So, whatever energy you are applying to the system is getting in terms of formulation of those new two surfaces, okay, along which the crack has actually formulated. So, in a single crystal level, if we wanted to gauge what is the strength sigma c of such a pair of surfaces created, the sigma c happens to be given by E gamma by d to the power of half, where E is the modulus of elasticity of the material, d is probably the lattice spacing. Okay. So, this is actually one lattice spacing. We are talking about crystalline materials, and particularly one lattice spacing in the cleavage plane, that is what is of concern to us. And think of it that in brittle solids the failures take place by extension of such cracks. So, therefore, there is, if supposing some kind of a twin surface pair is created, it basically extends itself in a certain direction, and we say that this is because of the crack propagation process. So, therefore, the along that particular line there develops several such interatomic spacings where there is a new surface which starts getting created. Okay. And so, there is a complete cleavage plane which is formulated, which may be more than a few lattice spacings in length. Okay. So, in that case, the sigma c which comes out, or the bulk strength of the material which comes out, is given by again E gamma by L to the power of half, where this L which I just told you is much greater than one lattice spacing. So, the crack is around, let us say 5 different lattice spacings, or even more, 50,000 more lattice spacings. So, it is a relatively larger entity in comparison to a single cleavage plane created across a single crystal, where the question is only of one lattice spacing. So, obviously, the sigma c reduces because of that, right. Sigma c in case of crystals is inversely proportional to d to the power of half. In this case, it is L to the power of half, and L is much larger than d. So, obviously, the sigma c would be much lower in case of bulk materials, okay, than in case of crystals. So, sigma c bulk is much lower in comparison to sigma c crystals. Okay. And so, that gives you a basis of why solid welding processes should happen. Okay. So, we have already seen in the first part of our lecture very appropriately that the failure of a polycrystalline ductile material is typically due to the movements of what we call dislocations, which may be available over only 1 or 2 or maybe a little more size lattice planes, and these planes are sort of misfitted into the overall lattice, because of which you can say that there is a tendency of the failure of the polycrystalline material. So, if all the dislocations move together in certain space, there is a tendency of the energy in that region to go high, because of which the material will start breaking down, and there is plastic instability because of this. Okay. So, the foregoing discussion indicates that the bulk strength of the material is much lower than the bonding forces of the constituent atoms. We just had an idea that in one case the total amount of ultimate yield strength sigma c is proportional to the inverse of d to the power of half, and another L to the power of half, and L is very greater than d. So, sigma c obviously is lower in value in case of a bulk material. So, think of it that when we talk about a joint strength, it is about how the material would arrive at its ultimate yield strength when there is some kind of a crack or separation or something which starts taking place between the different planes of the materials. And in this particular case, we are talking about a situation where we are comparing the lattice misfits, okay, because of the pressure generated between two surfaces, where the distance is coming very close to that of almost a grain boundary. So, meaning thereby that the two surfaces that we are pressing in the solid welding is coming by a distance closer than almost 1 or 2 lattice spacings. So, obviously, that force would be much greater or the yield strength in that particular region, because of that lattice misfits of a few planes between the two surfaces, would be much greater in comparison to the bulk strength of the material. So, obviously, when in such a case, if we pull the material from both sides, the failure will take place along any other region of the bulk, but not on the interface. So, that is what the solid welding strength is defined as. Just because in a crystalline level the ultimate yield strength increases much more in comparison to that of a bulk level, you can say that a plane of lattice misfits because of this kind of a pressure, where both the surfaces come close by almost like a grain boundary thickness difference, is attains a much larger value in comparison to the overall bulk strength of the material. So, a good welding does not require to achieve a strength equal to that between the adjacent lattice planes, and you must remember that at room temperature, with negligible creep, even a plane of lattice misfit is not weaker than the bulk material. Okay. So, in a cold welded junction, it is essentially a plane of lattice misfit which is inserted between the two meeting surfaces at a huge pressure. And so, the contact, if we look at between the two planes which are being brought close together. Let us say we are welding these two surfaces with respect to each other, with respect to applying a vertical pressure in between the two. So, there are the small asperities between the surfaces which kind of formulate the real contact. Okay. And the metallic bridging kind of a thing happens here, that supposing there is one contact which is like a hill and another which is again like a hill. So, there is some kind of a when it joins each other, obviously the real area which is there, as I think I had earlier mentioned very appropriately in case of study of friction, is much smaller. So, the A real is smaller in comparison to the A apparent. The apparent area really is that of the surface, and the real area is very small. So, in this region it is very easy to come for the overall stress to come to the plastic deformation level, and there is some kind of a deformation of these two asperities which results in a cold weld. And because obviously you have brought them closer than the and so that the bulk strength is kind of exceeded at that particular level, and this metallic bridging occurs even though if there are some kind of an adsorbed surface layer like an oxide or some oil etc. present, still this metallic bridging occurs very well. Okay. So, the bridges so formed have the property of a true grain boundary, and hence they are stronger than the bulk material as I had earlier illustrated, and also there is some work hardening which takes place in the layers just beneath the mating surfaces. So, overall the weldment in this particular region, because of the work hardening underneath and the strength here of almost a single crystal, becomes much larger in comparison to the bulk strength of the two materials sigma c. So, therefore, it is considered to be a good weldment. So, let us look at the series of events which happen in such processes. So, if we consider sigma y to be the bulk strength of the material, or let us say the yield strength of the material, and we apply a force P e over these two surfaces which we are bringing close to each other. So, this force is P e. So, obviously, the fraction of the area which comes in contact by formulating the weld can be easily given by P e by sigma y. Okay. And however, around the welding zones, if I look at really how this asperity is getting deformed. So, the asperity earlier was present like this, and when we have touched the asperity, the slight deformation happens, okay, and then there is some kind of a local weld which has taken place here. So, there will be some area which will come in contact without the actual flow as well. Supposing there was an area just close by where the height was not so significant as the plastic flow would happen. So, supposing these two get welded together, then it may be possible that these two just about start touching each other very close to the surface here. Okay. So, there is obviously quite a bit of that area which is not so high, so that plastic deformation would occur, but still they will touch each other when the plastic deformation may happen across some of the let us say top order asperities with higher heights or higher larger heights on the surface. Okay. So, here we can obviously say that these areas which have just come in contact without any plastic flow would still be in the elastic region. So, this is a elastic region, okay, and this obviously is a plastic region. And so, really whether the two surfaces would separate off from each other would depend on whether these elastic forces are greater enough to pull apart the plastic deformation and weldment which has been formulated. So, if this area were very high, in that event obviously the surfaces would come closer, but the elastic range material, if it is not able to give sufficient amount of recoiling force, so therefore, it will not really change anything, and the weldment will remain intact. So, experimental results suggest that if you include this area, the total area of physical contact with moderate external pressure comes out to be about close to only twice P by sigma y, right. Sigma P by sigma y was the area which was the plastically deformed asperity area, but the overall area then becomes twice P by sigma y. When the applied load is removed, the two surfaces separate out only when the elastic forces trapped in the region around the bridges are strong enough to break apart these metallic bridges. If it does not happen, the weldment would remain as such. So, obviously, for softer materials where the deformation level is much higher, it results in a better or a permanent adherence, because more or less this elastic force may not be that critical, as the number of areas which would have yielded to the plastic range would be much higher in a softer material than in a harder material. So, in the solid phase welding process, 4 most important phenomena or factors are associated. One is obviously the surface deformation, the other is surface films, which sometimes promote or heed, or which sometimes promote the separation between the surfaces and does not allow the contact to take place. It may be a brittle film, for example, an oxide film, where there may be some local crack propagation which happens, where this strength aspect of bulk versus weldment, that theory may not hold true anymore. And then there is also recrystallization, which may happen because of pressure driven heating of or pressure driven deformation of the different grains, and then obviously diffusion, which is migration because of concentration gradients between the two surfaces. If one surface has a higher concentration of a certain material in comparison to the other, obviously there would be some diffusion through the solid state happening when it comes closer to each other. So, the surface deformation that takes place during welding is quite difficult to measure, although some estimates can be brought out, and as such in pressure welding the bulk deformation is used as an index of the surface deformation. So, if I say for a sheet of original and final thicknesses Ti and Tf, I want to measure the bulk deformation, I would simply write this as Ti minus Tf per unit Ti expressed as a percentage, and for a sheet of or for a circular specimen of original and final diameters, for a circular specimen of original and final diameters Di and Df, this respectively would become Df square minus Di square by Df square as a percentage. Okay. So, that is how you express the surface deformation of either flat sheets or round objects. The strength of a welded joint increases with increasing bulk deformation, and no weldment would take place below a certain critical deformation happens, and the amount of deformation necessary for obtaining a specific strength decreases with the temperature increase, and obviously a strong weld may be made only with 10% deformation if the working temperature is quite close to the melting point of the material. Also, the ratio of the oxide hardness and the parent material hardness effectively governs the amount of necessary deformation which would happen in solid phase welding. So, the greatest hurdle which comes in case of solid phase welding are the oxide layers, and so what and or maybe some kind of oil films or some kind of separation films which would not allow the weldment to happen by making an intermediary layer, either which would have crack propagating effect or would probably have some kind of oil or impurity, not allowing the two materials to come to the closeness of that of a grain boundary. So, the many methods which are used for taking care of such situations. For example, you can scratch brush the oxide layers on the top of the surfaces which you want to solid weld in this particular manner, so that you still have you expose the material below it, or maybe either with washing techniques or with some kind of etching techniques, remove away the layer of lubricant or the layer of the oil which happens to be a part of the sheet because of its forming process associated with the easier dye removal, etc. So, there are many ways of sort of ensuring that you do not have the oxide or the intermediate oil layers for doing a good solid phase welding. So, we would like to continue further in this area, but in the interest of time I would like to close this particular module. In the next module we will talk a little more about just extension of whatever we have studied so far, followed by studying of different sources which would be important for us to analyze the liquid state welding particularly, and sources of heat would be something like, let us say, electrostatic arc welding, and how do we really design for a good power system, etc., which would do the welding properly and effectively. With this, I would like to end this particular module. Thank you so much for listening.